So regarding the Q&A, for sure, I will do all my best to have this course continued and such a way that we can cover at least a significant part of ARFCAN. Based on the speed that we do have right now, I'm expecting that we will be able only to go to the curve space and touching a little bit on the matrices, not going through the group theory and special function. But for sure, I will try all my best to have the second course and even maybe the third course going through the complex analysis, going through the group theory, special function, and also differential equations, and deep down into some of the examples like the variations and scattering theory. So I will do all my best to teach this, but in winter I have to teach the course of electrodynamics at the University of Ottawa, so it will take time. Okay. Can you hear me?
Yeah.
Yep.
Okay, perfect. So I think now we are okay. We are starting with 15 minutes delay, and my apologies that was some technical issues. If there is any question related to the previous course, please let me know. And if there is not, I want to correct myself that there was a mistake that I said during the second lecture. When we had A cross B cross C, by mistake I say that when A is in the plane of B and C, that is equal to 0. And that was my mistake, and my apologies for that. I think I got confused with A dot B cross C. So I will make a note on the video on the YouTube one, such a way that this error will not be propagating anymore. So let's go back to the course. So if you recall. Well, we worked with the scalar function of x and y and z, and we say that this scalar function, if you do a rotation, is still the same. Okay, that is true that the coordinate is changing from, let's say, x and y to the new coordinate of x prime and y prime, which is rotated by the angle of alpha. But still, the quantity of a scalar is the same. So, for example, if you assign a temperature here, in my coordinate, this temperature is the same. If someone is rotating their head, they were expecting to see exactly the same temperature, although it's a new coordinate for them. And we say, let's take the derivative of that. And what we have done, we took the derivative, and what we realized the derivative with respect to any of those x. And we say, well, it's better to not use x, y, and z, but it is better to use x1, x2, and x3, and even you can extend it to n-dimensional space. Why we are using this? Because that allows us to essentially compact the mathematics, okay? Mathematics, and essentially we can also do some generalization. So if you do take the derivative of phi prime, let's call it x prime, y prime, and z prime, with respect to x prime, okay, then you have to take the derivative of, since the phi prime is identical to phi, we replace it with x, y, and z, and then you have to take the derivative with respect to x prime. And indeed, what we realized that, well, the result will be the partial derivative of phi with respect to x, derivative of x with respect to x prime, and partial derivative of phi with respect to y, derivative of y with respect to x prime, and etc. Okay, z and derivative of z with respect to x prime. So from this, we made the generalization, and we say that if you take the derivative of phi with respect to x prime I, which I now is an index which is changing from 1 to 2 and 3, then what we will get using the chain rule, we will get Aij derivative of phi with respect to xj. And we, from here, we introduce an operator. And this operator was a derivative with respect to xi or xj, doesn't matter. So which means that this is indeed is x hat derivative with respect to x plus y hat derivative with respect to y plus z hat derivative with respect to z. And that is in, remember, is in the Cartesian coordinate. And we say that we call these, indeed, we call these gradient, and we have a label of a vector. Why? Because if you do a rotation, you will see that this vector is following exactly the vector rotation. So indeed, if you define this as a new vector of a, I think last lecture I used the word the calligraphic of a prime I, and we say that this is identical to aij aj. And well, here we introduce the gradient. So the gradient, which is nabla, as I say, that you can call it del, or you can call it nabla. And the definition that we use for this in the Cartesian coordinate is derivative with respect to x, y hat derivative with respect to y, plus z hat derivative with respect to z. Okay. And remember, also gradient can be defined in n-dimensional space. So in n-dimensional space, gradient can be determined or defined as x hat 1, which is a unit vector along x1 axis, derivative with respect to x1 plus x2 hat derivative with respect to x2 plus x3 hat derivative with respect to x3 until you will go to xn hat derivative with respect to xn. And as I said previously, mathematicians, we don't like to carry on partial derivative with respect to partial derivative of x1. And we say that for simplicity, we write partial derivative with respect to x1 as derivative of 1. Okay, so we write it as x1 derivative of 1 plus x2 derivative of 2 plus x3 derivative of 3 plus x hat n derivative of n. Okay, that's a compact form that we do have. So that was the generalization of a gradient. And what was the physical meaning for the gradient? I mean, you know, of course, you can define mathematics, and mathematics is wonderful. Physicists, we look for the meaning. We say that if you assume that you have a surface, which this surface is determined by the function of phi that you have, which is x1, x2, x3, even if it's an n-dimensional space, you can call it also xn, then you can assume that 2 points you have it. One is located here, and then you can look at the infinitely small displacement here, which is, you call it dr, and dr indeed is given by x1 hat, dx1 plus x2 hat, dx2 plus the other, which is xn hat, dxn. And now what you look for, you look at gradient of phi, which is what you have it here, dot dr, which indeed, if you do the mathematics, which is coming from infinitely small changes of d phi, indeed you will get d phi. We proved that last time. And we say that if that dr is laid down in the same plane of the same phase, which we call it phi is a constant value, then indeed what you will get from here, you will get the gradient of phi dot dr is equal to 0. So which means that the gradient of phi is orthogonal to the dr, because dr is an arbitrary vector which can be in any plane. So gradient of phi indeed orthogonal to the dr. So this is the way that you will find a normal to a surface. So you assume the surface, you write the equation, and then what you have to do, you have to take a gradient of that. And what is the orientation? Because I mean, as I say, this is orthogonal to the surface of phi constant. But what is the direction of that? So the direction, as you recall last time, as I say, that the direction will be towards a greater phi. Okay, so if you have, what does it mean? That if that's a surface of phi, which is equal to C1, and that's a co-surface of phi equal to C2, if C2 is greater than C1, then definitely gradient is in this direction, is normal to that, but also is towards increasing the phi. Okay, so that was the definition of a gradient. And I made an example last time. I said that, well, assuming that this co-phase is given by is only one function in the three-dimensional space. So phi x, y, z is equal to r, which r means that is equal to x power of 2 plus y power of 2 plus z power of 2. So, or you can write it as a x squared plus y squared plus z squared power of 1/2. And now, if you look at the phi constant, what does it mean? That phi of x, y, and z is equal to a constant of CTE, which means that r is equal to a constant of c. Then if you plot these in the three-dimensional space, indeed, that will be x, y, z. That shows a sphere in that space. And this sphere has a radius of c, which is this value that you have. Now I am asking what is going on with the normal to this surface, how to find normal to this surface. Indeed, I have to calculate the gradient of phi. So the gradient of phi then will be x hat gradient derivative of phi with respect to x plus y hat gradient of phi, derivative of phi with respect to y plus z hat derivative of phi with respect to z. And then I have to do the calculation, and I have to find each of these terms based on the functionality of phi. So phi x, y, and z is equal to r, which r means that is equal to x squared plus y squared plus z squared power of 1/2. Then I'm looking at the derivative of phi with respect to x, which means that I have to take the derivative of x squared plus y squared plus z squared power of 1/2. And if you take this derivative, the result will be 1/2. First, you have to take the derivative of that, and then taking the derivative inside of this, which will be 2x, then multiply by x squared plus y squared plus z squared power of 1/2 minus 1. So if you simplify this, 2 goes away with the 2, and then you will get x multiplied by x squared plus y squared plus z squared power of 1/2 minus 1 will be equal to minus 1/2, which means that that is x multiplied by r power of minus 1, which is x divided by r. So in a similar fashion, you can take the derivative of phi with respect to y, which is y divided by r, because x, y, and z, if you see they are all symmetric in this fashion, derivative of phi with respect to z also is equal to z divided by r. So if you replace all of them inside of the gradient of phi, which is x hat derivative of phi with respect to x plus y hat derivative of phi with respect to y plus z hat derivative of phi with respect to z, then what you will get x hat x divided by r plus y hat y divided by r plus z hat z divided by r. And x hat, the denominator is identical for all of them. I will factor it out. Then it will be x hat x plus y hat y plus z hat z. So this is indeed the r vector. So you will get r vector divided by its magnitude, which is a unit vector of r. So it shows that you have a radial unit vector of r hat, which is, of course, is normal to this surface. And remember, r hat is changing, right? R hat is like this here, r hat is like this here, r hat is like this here, and is not look like x hat, y hat, and z hat, which the axis or the orientation are fixed in space. So r hat, it depends on the position that you have it on the surface. It's always radially oriented, and then is towards a positive direction of r. So so that is what you will get, and we can go with other examples if you want. I mean, someone can do looking for any arbitrary function of r, and then you can look at the gradient of this. So you will find the function. Well, so it's good, fantastic. So far, remember that this gradient, which I defined here, which was x hat again, derivative with respect to x, y hat derivative with respect to y, plus z hat derivative with respect to z. So this is, of course, is a vector, okay? It is a vector. But also, remember, that's also an operator. What does it mean? That, well, it is derivative, and these derivatives should act on something, should act on a special function, I mean, some specific function. So these derivative with respect to x, derivative with respect to y, derivative with respect to z should act on a scalar function, I say scalar function for the moment, okay? And at the end, we can even generalize this. Good.
Sorry, Abraham, to
Yes.
interrupt you. There's
No
a
worries.
quick question about one of the examples you brought up last time. That was about the wave vector. K
Okay.
is equal to gradient of phi. Could you please recap on that?
Oh, that was an optics example, right? So there is a beautiful paper by Sir Michael Berry about four momenta, if I remember well the title. And you can, if you have interest, you can go through this paper and learn more about the K vector or momentum of light. But one of the definition that I said is that if you assume in optics, if phase is given by a specific function, so I call it phi of x and y and z, then the propagation direction, K vector, this is what we call it, is given by gradient of phi. This is what I meant the last time, okay?
Perfect, thank you so much.
Of course, Nazanin, thank you. So let's go back to the gradient. So remember, as I said, gradient is complicated in some sense. The physical meaning is beautiful. is normal to the surface, okay? It's a vector because if you do the coordinate rotation, you will see that also that is changing, okay? Wonderful. But at the same time, it is an operator. So let's treat it like a vector for the time being. I have a vector of nabla or del or gradient or whatever you want to call it. And I have another vector of A, okay? Can I define a dot product between the two? I can do that, right? If anyone doesn't agree, just tell me. Okay, I'm looking at the Q&A. Do you agree that I can define dot product between these two vectors? Okay. Yes, all they say yes. Perfect. Also, I can write it in this way. I can write A dot del. Do you agree, guys? I can write it in these two formalism. But these two, they are not the same. Remember, okay? If you recall, we say that A dot B is equal to B dot A. But here, note that if I write del dot A is not identical to A dot del. And that's a difference that you have to be very, very careful. So let's look at the first version. The first version, which is divergence of A. What does it mean, divergence of A? You write x hat. Remember, always I write the vectors at the beginning, okay? X hat, derivative with respect to x, plus y hat, derivative with respect to y, plus z hat, derivative with respect to z. I'm writing it also in the Cartesian coordinate because it's simple. Dot ax, x hat, plus ay, y hat, plus az, z hat. Now, what I have these dot product with this one and that one. So let's do that. It will be x hat, derivative of x, dot ax, x hat. Okay, for the moment, I look only at the first term. What is the result of this? So the derivative is acting on these two terms, but x hat, this term, is a constant. Okay, x hat is a unit vector which is constant, is not changing, is not look like r hat, which we just derive. So x hat is a unit vector which is the magnitude and the orientation is fixed in space. So it's a constant. Derivative of a constant, of course, is zero if you want to take it, but derivative of a function multiplied by a constant, easily you can take the constant out of the derivative. So what you will have x hat, right, dot x hat, derivative of x of ax. Do you agree, guys? Any questions?
I don't think there are any questions.
Lovely. So what is going on with x hat dot x hat? So we did the calculation in the past is equal to 1 derivative of x of ax. Now I am assuming that a is a function of a is a function of x, y, and z. If it's not a function of x, y, and z and is a constant vector, definitely the derivative of a constant will be equal to 0. Okay, so if you do this calculation for the second term, what we will get, x derivative with respect to x of a y hat, and that will be x in the same formalism, y hat derivative with respect to x of ay, then what you will get, x dot y, that will be equal to 0. So that is 0. So if you do all of the calculation, what you will get, we will get the derivative with respect to x of ax, derivative with respect to y of ay, derivative with respect to z of az. Lovely. So we call these gradient dot a, we have a name for it, and we call it divergence. Okay. What is the result? A scalar quantity. Good? Perfect. Now let's look at the second term. Second, which was not identical to this, was a dot del. Okay? This has no name, by the way. It's just a dot product of a vector with nabla. So you can do the same calculation. What you will get here, you will get ax derivative with respect to x, ay derivative with respect to y, az derivative with respect to z. Of course, the result of these, depends on the function that you act on. Do you know what I mean? Means that if a dot del, which is an operator, acts on a function of phi of x and y and z, what it will be the result? A scalar. Okay. If that is acting on a vector, let's say v, then the result will be a vector. Okay. Any questions?
Someone is asking about a use of gradient in daily life.
Well, a gradient, if a force is a conservative, then definitely that can be explained in terms of a gradient of a potential. Okay. And that's a daily life use. So the potentials that we have, this is what usually we do. We either define a gravitational potential or electrostatic scalar potential of electromagnetic waves, and then from these we can determine the field, and then we can determine the forces. So that's a daily use.
Someone's asking, in divergence, ax and so on aren't scalars. Shouldn't it be 0?
Oh, not necessary. Not necessary, because ax. I will write it down here. So the question is that divergence of a is equal to, as we discussed, is derivative of x of ax plus derivative of y of ay plus derivative of z of az. Okay. So ax indeed is a function of x, y, and z. So the derivative exists. Maybe is 0, maybe is not 0, depends on the function. The same for ay, the same for az. So all of those AY and AZ, they are function of X, Y, and Z. Okay.
Can we say that operator is the quantity that can transform into vector or scalar depending on the type of the operator?
Exactly. Exactly.
Perfect.
Yeah, well said.
Can you explain the gradient of vector?
Can you explain the gradient of a vector? Yes. Be patient, Shagol, Rauf. We will discuss that in the end of the chapter 2. Yes. Gradient of a vector will be a tensor.
Can you explain what is del in a simple mind way? Is it a vector, an operator, and derivative?
So let's Nazan, if it's fine, let's stop here. Let's go
Okay.
with some of because there is some of the questions that are related to what I'm going to describe right now. Okay.
Perfect. Thank you so much.
Thank you. And so the divergence of A is given in this way, and as I say, is different from A dot del, which is AX derivative with respect to X plus AY derivative with respect to Y plus AZ derivative with respect to Z. Remember that should act on something, on some function. So that function can be a vector, can be a scalar, and depending on the form, the result either will be a scalar or will be a vector. Fantastic. Now let's go through the definition of, or let's say the physical meaning of a divergence. Okay. Let's go with an interesting example. So all of us, we have been in mountains or in the sea, and sometimes we will see water flowing on the ground, in the form of a spring or in the form of a river. And assuming one of those examples, so that's a river, so which water is flowing around. Okay. And now I'm asking you, assuming that we have a small volume inside of this water, okay? Inside of this river. Very, very small volume. Small volume of dx, dy, dz. That's a volume which I call dv. That I place it here is some sort of, let's say, mesh-like cube, which I will place it there. Okay. Now the question that I'm asking you is that what is the flow of water through this volume? Okay. So now I will enlarge this and I will plot it for you. Okay. So that is X, that's Y, that's Z coordinate that I have. And the box that we just discussed, this is the box that I have, is like this, like this, like that. And the length of these box along x is dx, along y is dy, along z is dz. So that's the size that you have it for this box. And indeed, the volume, as I say, is the area which is dx dy multiplied by dz, okay? So, well, water has a density, right? Water inside of this has a density which is x, y, and z. And point by point, this density can be changed, okay? That might not be the case that we have it in a river, but in the ocean, definitely yes, because if you go deep down in the ocean, you will see that the temperature is about 4 degrees, and usually that's a maximum density that you will get it for water. If you come to the surface, the temperature is increased, and then the volume, the density is decreased. And then for each point, as I said last time, look like a vector. Each of the, let's say, molecules of water, they have a certain velocity, which this velocity is given by x, y, and z. Is a function of the coordinate. And then this velocity is a vector. It can be in any direction. For example, here is in this direction. Here is in this direction. Let's plot it. Here is in this direction, the velocity. Here, the velocity is in this direction. Here is in this direction, and that direction, etc. So now I want to understand how much water is going through this, volume. Okay. So what I have to do the calculation and find out how much water is going through x directions, through y directions, through z direction. So indeed, the density x, y, z and velocity of x, y, z, that will tell me the flow of the flux of water in one specific direction, okay? So, for example, along x direction, I assume that I have, this is what happens. So, within certain velocity, water is entering here. And then the only component that contributes along x direction, along this, is the Vx. So the only contribution will be the Vx. And then what you have an amount of water which is coming from the back surface, which call it surface number 1, and the front one, which is surface number 6. Okay. So this surface on the back, I will call it surface number 1. And the surface on the front, I will call it surface number 6. Okay. So on the back side, on the surface number 1, rho of x, y, and z multiplied by v x, y, z, but only which component is important for us? Only the x component, because the other component, they are orthogonal to the surface. So only the Vx part is playing role. Then at the origin, because that's the place that the surface is located at origin, multiplied by the surface area that you have. The surface area, the length is dz, and this one is dy, so it will be dz dy. That will be the amount of water per second, which is passing through this surface. Okay, so essentially that's the water that is passing through this. On the other surface number 6, exactly the same situation happens, because the velocity of y, velocity of z, they will be orthogonal to the surface, so they will not contribute. And then what you will get, you will have rho of x, y, and z, again, velocity of x, y, and z. But now the surface is located not at the origin, but a little bit displaced. So it means that it's at origin, but displaced by dx. Multiplied by the surface, which the surface exactly is dy, dz. So along x direction, what you have that specific amount which is coming in, and along y direction, you have that specific amount which it will exit, or vice versa. It's up to you. It depends on the magnitude of Vx. It can be negative, it can be positive. But what is important that the subtraction of the two will tell us how much water exists inside of these. So indeed, indeed, for x direction, the amount of flux of water per second or per time, the flow of water per time or per second, is equal to rho of x, y, and z, Vx, x, y, and z at dx, dy, dz, minus rho of x, y, and z, Vx, x, y, and z at origin, dy, dz. So for people that they are familiar with the Taylor expansion, what I can do, I can expand this function close to the origin, because that's it has been just displaced by dx. So what I will do within the first approximation is rho x, y, and z, Vx, x, y, and z at the origin. Okay. Then you have the first derivative, which is rho x, y, z, Vx, x, y, and z, derivative with respect to x, dx, plus the other term, which I will neglect them because dx is small. This is what we assume, that the volume is extremely small. Then multiplied by dy, dz, minus the other term, which I have it just here. So the first term and the last term, they're identical. Okay. And what I will get, the result of these will be equal to derivative with respect to x of rho of x, y, z, Vx of x, y, and z, dx. Then I had dy and dz as well, dy, dz. So that is the flow of water along x direction. In a similar fashion, I can show that for along y direction, along z direction, which will be the total flux of water, will be equal to the total of water in the volume in all directions, let's call it, is equal to along x, along y, along z. So if you look at just if you do it as I say in the same way, you will get derivative with respect to x of rho of x, y, z, Vx of x, y, z, dx, dy, dz, plus that was contribution from x, that is the contribution from y, which will be derivative with respect to y in the same way, rho of x, y, z, vy, remember, x, y, z. And then here, what you will get dy, dx, dz, which is exactly the same. And finally, for the z direction, you will get derivative with respect to z of rho of x, y, and z, vz, x, y, z. Then you will get dz, dx, dy. So the flux of water and the flow of water per second per volume, flow of water per second per volume, which is again flow of water per second per dx, dy, dz is equal to derivative with respect to x of rho vx plus derivative with respect to y of rho vy plus derivative with respect to z of rho vz. Here, what I'm doing, I just omit the functionality of rho and v just for simplicity. Okay. Good. So, what is that? You can just type it in the Q&A. That's equal to the divergence, exactly, divergence of rho v. So, indeed, that's the physical meaning of divergence. The physical meaning of divergence is that it will tell you if you are creating something in a volume or you are taking something in a volume. Okay, and for those people that they know fluid mechanics, which is exactly what was the example here. If we assume that rho is not function of time, and velocity also is not a function of time, then definitely the divergence of rho v is equal to 0. So this is what we were expecting, and this is what we call it the continuity equation. You are not expecting that if you take these, let's say, box, you are not expecting that the water will be created inside of this. So whatever water is coming in, that will be exit, unless this box is located in a place which you have a sink, so it sucks water, or it's located in a place that you have a source of water. So that's the meaning of the divergence. So divergence will tell you what is happening with the source, either creating or the source that you are taking away. Well, an example of this in physics is the divergence of B is equal to 0. So what does it mean? That there is no net source for magnetic field. What does it mean? Magnetic induction of field, which means that there is no monopole. There is no monopole or magnetic monopole for magnetic field. Magnetic field. Okay. So if you look at the magnetic field, which is look like the vector that I shown for velocity of water, then what you expect that there is a continuity, and there is no places that these magnetic fields are created and the magnetic field are destroyed. Well, you can create magnetic field in any way that you want, but always what you have is a divergence of B is equal to 0. You cannot create it in even synthetically in the laboratory. These the laws of physics. So the divergence of B is equal to 0. However, divergence of electric field, can you tell me, guys, what is the divergence of electric field in electrostatic?
The charge density.
Exactly. Well, yes, you're completely right, Dr. Amir. But people, they say that is given by 0. No, it's not equal to 0. It's given by the charge divided by epsilon naught, right? Charge density per epsilon naught, which is the permittivity of the vacuum. So exactly, Goar and other people, they say correctly. So, but here, what is important that for electric field, what you're expecting that electric field is created in a place or can be destroyed in a certain place. So, for example, for the positive charge Q, what we have, that's a form of the electric field that you have it. As I say, these look like the spring and a place that you are creating the electric field. And while if you look at here, you have a divergence of E, which is positive. Here, the divergence of E can be negative, which means that it looks like a sink for electric field. It sucks the electric field. So the divergence of E is negative here. Okay, so that's the physical meaning for the divergence. So the divergence will tell you about the source of that vector. Okay, if it has a source or if it has no source, if the source is positive or the source is negative. Okay, so that's really an important concept that we have to be very, very careful with that. Good. Is there any question?
I think just a quick question. As the net flow is positive, then from where the extra amount of water is coming?
Yes. So the net flow is positive.
From where?
From, oh yeah. So it's coming from a source, indeed.
Okay.
It looks like having a pipeline going in, assuming that this surface that I have, excluding the pipeline, okay?
Perfect. I think that's all.
So someone says that what about dynamical electric field? Does it have a zero divergence? No, it doesn't have a zero divergence. No, we don't have that. Okay. Does divergence only used for the time dependent function? No, it can be used for the time independent as well. This was exactly the example that we had here. So the continuity equation that I had in general, if you assume that rho also is a function of time, then the continuity will be the derivative of rho with respect to time plus divergence of rho v is equal to 0. That's in fluid dynamics. Okay. So we had a scalar. We could create a vector with it by taking the derivative and building up a vector based on that. Now we took that operator and we did the dot product and we define if the dot product is coming from the right side as the left side, and we call these the divergence. Now we have another things that we can work with, right? Which is the cross product. So we have again gradient, which is our del operator, which is x hat derivative with respect to x plus y hat derivative with respect to y plus z hat derivative with respect to z. Again, guys, I'm repeating myself. Whatever I am doing here is for Euclidean let's say Euclidean coordinate, means that is a Cartesian coordinate. So x hat, y hat, and z hat, they are not coordinate dependent. So they are fixed in space. Okay. Now I can take another vector of A, which this vector, again, remember, is not a constant vector, is a function of x, y, and z, which means that each component of it is a function of x and y and z. So take the gradient and do the cross product with A. Again, remember, this is not identical to a cross product of del, okay? These two are different. What are the difference between the two? So remember, again, here, these gradient, or let's say nabla or del, should act on something. Here, no, it has already acted on A, okay? So these are the difference between the two. Let's calculate the first one. Second one also is important in physics, is extremely important. Out of the scope, okay. So look at the gradient of, the curve of A. I already say curve, but let's look at the gradient cross product of A, and let's do the calculation. So, well, how do you do the cross product? You write x hat, y hat, z hat, and then we write the component of these vector first, which is derivative with respect to x, derivative with respect to y, derivative with respect to z. And then we write the second vector, which is ax, ay, and az. But remember, del here is acting on A. So let's expand it. If you do the expansions, it will be, the first one will be x hat, derivative with respect to y, derivative with respect to z of ay, az, minus y hat, derivative with respect to x, derivative with respect to z of ax, az, then plus z hat, derivative with respect to x, derivative with respect to y, ax, ay. Now I have to we have to do the determinant, so it will be x hat. So derivative of az with respect to y minus, in the normal way you write it, ay derivative with respect to z. But remember that nabla is always acting on A. So the correct form is writing derivative with respect to z of ay. Okay? That's really important. Then we write minus y hat. The same way here will be derivative of az with respect to x minus, and the second one will not be ax derivative with respect to z, will be derivative with respect to z of ax, and the same way for z hat, which will be derivative with respect to x of ay minus derivative with respect to y of ax. So the result of this is a vector. And this vector also has a very interesting physical meaning, and it's really important to understand the meaning of them. Before going through the calculation of these, let's calculate A cross del, which in the same way, we have to write it as x hat, y hat, z hat. First, the vector of A, we have ax, ay, az. Then we have a vector of nabla, which is derivative with respect to x, derivative with respect to y, derivative with respect to z. And then we do the expansions. It will be again the same way. Ax, will be ay, az, derivative with respect to y, derivative with respect to z, minus y hat, derivative with respect to y hat, derivative with respect to ax, az, derivative with respect to x, derivative with respect to z. I will not write the rest, so I will just simply ax, ay, derivative with respect to x, derivative with respect to y. Now let's do the calculation of the determinant. So here you will have ay, derivative with respect to z. Then here you don't write it derivative with respect to y of az. So why? Because you will see that nabla here, del, is not acting on a. So here you should arrange it properly. You should write it az, derivative with respect to y, and plus the other term. So it will be minus y hat, az, derivative with respect to x, minus ax, derivative with respect to z, and finally plus z hat, ay, derivative with respect to x, minus ax, derivative with respect to y. Good. So remember, a is ready to act on a function. This function can be scalar or can be even a vector. It's up to you. And you will see on this side as well, the result is again an operator, but is a vector operator already. Okay, so the result is not look like the a dot nabla, but the result is a vector operator. Okay, so I think that is clear that now we have these two different cases. Good questions?
Someone is asking about the example you brought up from fluid dynamics. I'd say probably it's not in the scope of what we're discussing right now.
D rho dt is
Yeah.
so that is not equal to k, is equal to 0. Okay, and they call it continuity, and we do have the same equation also in electromagnetism, so which is the continuity of the charge. And I will try to drive these for you maybe in this lecture or next lecture.
Perfect. Someone else is asking, is there any simpler way to link the geometrical intuition and the mathematical approach of divergence rather than the flow example you went through?
Yeah, there is another way which I will describe this in next lecture, which is the integral formalism of the divergence. So you can look at the divergence from the integral formalism and see it. So we will go through these for sure.
Perfect. Thank you so much.
Of course. So let's go through the curl. Okay. So we distinguish the two cases of A cross del and del cross A. Del cross A, we call it curl of vector A, or simply curl of A. Even in old fashioned, they write really as a curl A. If you look at the old books, you will see sometimes. And previously, as I say, that the divergence of A, you write as divergence of A, or div of A. In some book, you will see that this way. Or we have the gradient of phi, and we say gradient of phi, or grad of phi. In old book, you can see it as a phi. Or some people, they write it as a curl of A this way, or div of A. Oh, sorry. Okay. So let's look at the curl of A, and the result again is a vector. But let's look at the meaning of this. Again, fluid dynamics is a wonderful example. So assuming that I can look at the rotation of a specific function or vector of A on, let's say, in these coordinates. So let's plot it. So I have a coordinate, which this coordinate is X and Y. And here, I have a certain closed loop, okay? I call this loop of A, B, C, and D, okay? And I have a vector in this space, which this vector is a vector V and can have, is position dependent, X, Y, and Z. So it means that it has an X component, Vx, Vy, Vz, but also depends on the place. So it look like the fluid mechanics that I say, look like water. Each molecule can have a different velocity in different direction. This is what you have. And now what I will do, I will look at the rotation of vector V, which is vector of X, Y, and Z, on this loop. On this loop. Now I have to determine which direction I'm going to do the rotation. I will go counterclockwise. So I will go around this in this way. And A is located at the position of x0, y0. That is located at the position of x0 plus dx and y0. And D is located at the position of x0 and y0 plus dy. And finally, the last one, C, is located at the position of x0 plus dx and y0 plus dy. Okay, good. What I do now, I will do the calculation of rotation. So it means that I will do the integral of v dot dr on this closed loop. Okay. And remember, dx and dy are really small. And what I'm doing essentially, I'm doing the rotation of vector v at the close point of x0, y0. Okay, this is what I mean. So if you assume dx and dy, they are small. So now, if I look at the rotation of this vector, and note that also dr is infinitely small or incremental displacement, which is a dx x hat plus dy y hat, and also dz z hat, which if someone wants to expand it, yes, they can write it in this way. But we are in this plane, so it means that, well, we don't have the dz, so essentially it is equal to 0. But in general, it can be in the three-dimensional way. And now I'm looking at integral of v dot dr on this loop. The loop that I have, it is here, going here, going here, going here. So it will be the integral on, let's say, A to B, V dot dr, plus integral of B to C, V dr, plus integral of C to D, plus integral of D to A. So that's the rotation essentially, which I have it, right? Questions? I think we agreed on that. Good. So for A to B, what is the displacement? What is the dr, the value of dr? What is this dr? Is only changing along x direction. So dr will be x hat, dx hat, dx, right? Do you agree? For dr from B to C, it will be along y direction, will be x hat dy. Sorry, y hat dy. And for dr, remember it's coming from C to D, so the displacement will be essentially x minus dx, because it's coming back. And for D to A, that will be equal to y hat minus dy. And now, what else do I have? I have to evaluate the vector v on AB, BC, and CD and DAD. So what is the value of vector v on the path of A and B? So on this vector v, indeed, it is given by vector v, the value at x0, y0. Remember, there is a dot product here. And what is the value of vector v for the path of B and C? Approximately, since only the small displacement happens along y direction, that will be equal to v at x0 plus dx and y0 dot product with the value that we have. For the path of C to D, you can have two choices. You can write it as x0 plus dx and y0 plus dy, but remember it's a dx, dy, they will be small, and later on I will do the Taylor expansions. So then you have a second term which will be dx, dy dependent, which can be neglected, but essentially we can go with the inverse approximation as x0 and y0 plus dy dot. And finally, for the last point will be v of x0 and y0 dot. Okay, so let's simplify this together. V dot x will give you only the x component of x0 and y0 dx. What about this one? We will have plus vy, because the dot product with y hat will give you vy, x0 plus dx and y0 dy. And finally, that one will be v of x0 and y0 plus dy minus dx. And the other one will be dot product with y hat will be vy of x0, y0 minus dy. Good. So dx, dy, they are small, dx, dy, they are small, this is small. So what I can do the Taylor expansion of these. So it means that you have vy at x0 and y0, then you have the second term, which means that you have the derivative of vy with respect to the first argument, which is x, at x0, y0, then you have dx, dy. You can do the Taylor expansion for that one as well. What you will get vx x0, y0 plus derivative of vx with respect to the second argument, which is this one, y at x0, y0, then you have dy, then you have dx. So let's do a little bit of calculation and simplifying these together. So you have vx dx. Now I take away the x0 and y0. Then the second term will be vy dx dy. Sorry. Vy dy. Then I have derivative of vy with respect to x dx dy plus vx dx plus there is a negative sign here, by the way, minus this derivative of vx y dx dy, and finally I have minus vy dy. So this term, this term will go away with this term. This term will go away with this term. So finally, I have two terms only, and dx dy, they can be factored out. So you have the derivative of y with respect to x minus derivative of vx with respect to y dx dy. So the integral of v dot dr on the loop will give us vy respect to x minus derivative of vx to y on dx dy, which this dx dy is the surface of the loop. And indeed, this integral v dot dr, which is the rotation on the loop, divided by the surface dx dy, is given by derivative of vy x minus derivative of vx y. So here the loop was located in xy plane. It was like this, right? So, and that was the dx and that was dy. So, and if you use the vector dx dy and building up another vector based on the cross product, so essentially normal to this will be, that's a normal, by the way, means that there is a vector orthogonal to that one, which has a dx dy, and then along z direction, that is the surface vector. That tells you that is the rotation that you have it. So the rotation is indeed along this z direction, and that's the amount of rotation. Okay. Look at the meaning of this. So, and that is the third component of curl of V, or the Z component of curl of V. so what happens? Yes, please. So what happens indeed? If you have a vector, and if you look at the curl of the vector, indeed the curl of the vector will tell you what is going on with the rotation in that specific plane or along the axis which is orthogonal to that plane. So assuming that, again, look at the fluid mechanics that we had. So assuming the water is going around, okay. And then that's in the 2D plane, by the way, that's in the plane of X and Y. Now I have one of those pedal wheel. So you know the pedal wheel that we have. So people, they use it in turbines, for example, to creating electricities. Okay. So I'm terrible with the drawing. So it's one of those pedals. So I think you got that. You understand what I mean, right? So if you place one of those pedals here, then definitely that will start to do a rotation around this axis if the curl of V, which is the velocity of the vectors here, curl of V, the third component is not equal to 0. So indeed, the curl will tell you what is going on with the rotation. And this rotation has 3 axes: x-axis, y-axis, and z-axis. So indeed, that's the reason that you have 3 components there. So the physical meaning for the curl is the rotation along specific axis that you are looking for. So it happens in physics that sometimes the curl of a vector A is equal to 0. We call it a rotational. Okay. Good. Any questions?
No questions.
Even not from moderators. Okay. Good. Let me see if I have something else. Yeah. So far, note that we had gradient of phi. We have divergence of A, and we had the curl of A. Definition, that was normal to the surface. Divergence was a source of vector A. Curl was rotation of vector A. Rotation, of course, is a vector. Source is a scalar. Good? So I see questions.
Does the direction of V, the vector, change due to the rotation after applying curl?
Well, does the direction of vector V vector change due to the rotation of the applying the curl? Well, the rotation, well, if you apply the curl on a vector, that's completely new one. Is a new vector. It's completely independent of. It's completely a new one. With the derivatives is linked to the component of vector A, but is a new one.
Perfect. I think that's all.
Okay. Someone is saying that, well, sorry, I didn't get my answer.
We'll find the question and let you know later.
Okay. Thank you very much. Thanks a lot. So let's do a few other examples. So assuming now I have I have dots, I have cross. Now let's go with the triple products and see what else can we build up with that. So what happens if I take gradient, okay? I take nabla or del, and I do dot product with itself, okay? So we call these Laplacian, is a new name, okay? Laplacian. And what are you expecting? Is a scalar quantity, is a vector quantity? Can you type in the chat or in the Q&A? Scalar, be careful. They say vector, okay. Oh, all right. So Muhammadi is completely right. Ali also is right. So Shaho as well. So this is an operator, And remember, an operator depends on what he's acting on, exactly like Amir Hossein mentioned. So these result depends on what are you going to act on. If you are acting on a scalar, of course, the result will be scalar. If you are acting on a vector, the result will be a vector. If you are acting on a tensor, the result will be a tensor. So, but what is the value of this? I mean, let's look at the calculation. And Laplacian has a really important role in physics, okay? So you take the x hat derivative with respect to x, plus y hat derivative with respect to y, plus z hat derivative with respect to z, and then you do a dot product with x hat derivative with respect to x, plus y hat derivative with respect to y, and plus z hat derivative with respect to z. So we have x dot x, which is 1, x dot y is 0, x dot z is 0, y dot x is 0, y dot 1, y is 1, y dot z is equal to 0, and etc. So the result will be second derivative with respect to x, second derivative with respect to y, second derivative with respect to z. This is wonderful. Okay, and that is what we call it Laplacian. So remember, that shows up in physics, divergence of gradient of phi, and we call this Laplacian of phi. What does it mean? Is the second derivative with respect to x plus second derivative with respect to y of phi, second derivative of phi with respect to z. Or sometimes people, they write it in this way. Of phi. Remember, phi is a function of x and y and z. Or maybe that is acting on a vector, okay, of vector A. Or you can write it as Laplacian of a vector A. So that, what does it mean? Then you have Laplacian acting on AX, x hat, AY, y hat, AZ, z hat. Remember, A is a function of x, y, and z. Okay, so it's not a constant quantity. Then Laplacian will be linear. It will be AX, x plus Laplacian of AY, hat plus Laplacian of AZ, z hat. And the result of these, Laplacian is a derivative. Remember, is a second order derivative. X hat is a constant, so it will be outside of this. It will be x hat Laplacian of AX plus y hat Laplacian of y plus z hat Laplacian of AZ. Okay, so indeed, the Laplacian of a vector will be a vector which each component is a Laplacian by itself. Okay, And that's also important. Okay, good. Let's go with another example. Let's do the calculation of, I take two gradients, I will do the cross product. Okay, what's that? Is a scalar, is a vector, is what? Again, is an operator. Is an operator. Let's do the mathematics. So you will have, I will write it down. It will be x hat, y hat, z hat, derivative with respect to x, derivative with respect to y, derivative with respect to z. I will write it in I will write it in a short form. X, y, and z. Then let's do the expansion. It will be x hat, and that will be derivative with respect to y, derivative with respect to z, derivative with respect to y, derivative with respect to z, minus y hat, derivative with respect to x, derivative with respect to z, derivative with respect to x, derivative with respect to z, plus z hat, derivative with respect to x, derivative with respect to y, derivative with respect to x, derivative with respect to y. Okay, what is happening with this one? It will be x hat, and you do the determinant, you will get derivative with respect to y, derivative with respect to z, minus derivative with respect to y, derivative with respect to z, minus y hat, derivative with respect to x, derivative with respect to y, z minus derivative with respect to x, z, derivative with respect to x, plus z hat, derivative with respect to x, derivative with respect to y, derivative with respect to y, derivative with respect to y. What is the result of this, guys? Can you type it? I'm seeing Baran Shagol, okay. Shagol say that is 0. Any thoughts? Any other thoughts, guys? What it will be the result? If the function that you are acting on has no discontinuity, is continuous, then derivative with respect to yz and yz, they are the same. Xz, zx is the same. Xy, yx, they are the same. So indeed, the result will be equal to 0. Okay? So curl of gradient of phi, if phi is a well-behaved function, which means that there is no cut, there is no discontinuity, is equal to 0. So remember that curl of a gradient is 0. Curl of a gradient is equal to 0. That's important. Okay. So in electros, do you remember Maxwell equation, guys? So we had curl of E equal to 0 in the electrostatic. Okay. When curl of E is equal to 0, then E can be written as gradient of a scalar. We'll put a minus sign here just to make sure that we have the proper potential definition. Okay, that is one of the products. Okay, so the other one that we deal with is divergence of a curl. So you have a curl, which is a curl of a vector, which is a vector. And now I'm taking the divergence of that. What will be the result? Okay, Mason says that is 0. Whom else? So what does it mean? So you will get the divergence of x of curl of A, the x component, plus derivative with respect to y of curl of A, the y component, plus curl derivative with respect to z of curl of A, the z component. So derivative with respect to x of the x component of these will be derivative with respect to z of ay minus derivative with respect to y of az plus derivative with respect to y of the y component of that will be z ax minus derivative with respect to x of az plus derivative with respect to z of the z component derivative with respect to x of ay minus derivative with respect to y of ax. And if you simplify these, you will get second derivative with respect to x of z ay minus second derivative of az with respect to x and y, then plus derivative with respect to y and z of ax minus second derivative of y and x of az plus second derivative of z and x ay minus second derivative with respect to z and y of ax. So look at the term. So this term is identical to this term with a negative sign, so they will cancel out each other. This term, ay, is identical to this term, and again is equal to 0. And finally, this term is identical to that az. I did a mistake in the minus sign. For sure, it's equal to 0. Okay, guys. I think I have done a minus sign mistake. So derivative with respect to y of that, the y component will be z x xz will be negative sign. The x component will be z y yz. So that should be equal to 0. So I have done a mistake in the minus sign. So
yeah, I think it's the second term that has the negative.
which term?
So like curl of a y.
Curl of a y, okay.
Shouldn't that be derivative of x of az?
Oh yes,
Anyway.
yes. There is a minus sign here. Thank you. Thank you very much. Yes. Okay, so the result will be equal to 0. What else? Of course, this is what I have done, and usually myself, I prefer to do all of those calculations using the Levi-Chita notation, and this is what I have done previously for you guys. But sometimes it's good to do the calculus in this way. When we go to non-flat geometry or curve coordinates, I have to do the calculation in a proper way. So which is the Einstein notation essentially, which I will introduce later on. What else do I have? So we have another one which is very, very important, is a curl of a vector. That is really important. And how that works. So remember, the two derivatives, the gradient or del, they will act on a vector of A, okay? And in the past, we had A cross B cross C. If you remember, that was the triple product. And here we say that B cross C will be a vector orthogonal to B and C, and A cross B will be another vector which is orthogonal to A and B and C. Okay, it's orthogonal to A and the result of B cross C, which means that it will be in the plane of B and C, and then we use the backcap rule, so which was B A dot C minus cap, which was C A dot B. Okay. Here we can use the same rule. So we have A cross B cross C, and let's go with the vector V just to not get confused too much here. So let's use the backup. Backup says that you have B A dot C minus cap, which is C A dot B. Let's do the same. B is nabla, so it will be nabla acting on back A dot C, which will be dot V minus cap, which is V del dot del. Okay, this is what we will get just by following the backup rule. But know that here, the two operators of nabla, they're acting on vector V. Here, the vector V is on the back of the Laplacian, because if you recall, this was a Laplacian. So what we have to do, we have to move these to the front. So essentially, that operator should act on something. So on the vector V. So that was written by, that we can write them down as a divergence of V minus del dot del, which is Laplacian acting on V. So indeed, the result of curl of V is equal to gradient of divergence of V minus del dot del, which is again Laplacian of V. So is gradient of divergence of V minus Laplacian of V. Okay, and that's really important. It is very important identity. Okay, questions?
Okay, there is one question from way before.
Okay.
About the loop you were considering for curl. Someone's asking, why didn't we use x naught plus dx and y naught plus dy for d to a?
Oh, you can do that, but as I said, I mentioned this previously. If you do this, you have to do the Taylor expansion twice, and then that term slows down because you have a dx dy, another dy. When you asymptotically putting dx and dy both to going to zero, that term is not contributing. You can do that. You can do that. I mentioned that if you look at the video, if you look at the YouTube video, you will see that I mentioned explicitly. So
Perfect, thank you. If curl is rotation of a vector field, can it be related to a rotation of a circle's circumference? Is there similarity between them, or they're different?
Yes, indeed, it can be linked to that one. So you will see also we will use the Stokes theorem, and we will describe some of those properties in terms of the rotations and on a circle as well, which goes, if you consider small circles, indeed each of them they have some rotations, but if you apply it to a surface that goes to the perimeter, and then it's causing a rotation on the perimeter. Yeah.
Perfect. As the curl indicates rotation, if curl of x is constant in a physical system, does that mean vector x rotates with respect to a uniformly rotating axis?
If curl, well, yes, indeed. So the first curl will give you a rotation, and the second curl will tell you what is going on with the rotation of the rotation. Yes.
Perfect. This question was about one of the equations you've written. Curl of E is equal to minus partial derivative of B with respect to T. But I think you wrote not right next to it that it's what you've written is for electrostatic. You wrote that curl of E is equal to 0. It's because we don't have any time dependency.
Yeah, exactly. I have explicitly mentioned that that's for electrostatic, is not for electrodynamics. So electrostatic means that there is no time dependency. If there is no time dependency, curl of E is equal to 0. But if you consider time dependence, as you properly mentioned, yes, you need to have, you should consider also the derivative of B with respect to time. Yeah.
And the last question, can you please show one of the calculations using Levi-Civita notation?
100%. Which one? Which one do you want? So, okay, let's go with the curl. Okay, so curl of a vector A. If I look at the i's component, it will be epsilon ijk. Derivative with respect to j, okay, and then ak. Summation is on j and k. Remember, derivative with respect to j means that the derivative with respect to xj, okay? Good. So, well, if I don't know which one you want me to do, but I can do the calculation, for example, for one of them. Are you looking for the divergence of curl of A? Let's go with this way, right? The divergence of any vector V is equal to summation on I, derivative with respect to I of VI. So that means it is a summation on I, derivative with respect to I of curl of A, the IS components. And that is equal to summation of I, derivative of I. The curl of I, which I mentioned here, is given by summation on J and K, epsilon I J K, derivative with respect to J and AK. Okay? And that is equal to summation on I J K, epsilon I J K, derivative of I, derivative with respect to J of AK. Okay? So, and then I can write this as, by the way, this is a special case, which is a beautiful one. So if you look at this, these two are interchangeable by changing the index of I and J. So what I can do, I can change the index of I. So it will be epsilon I J K, derivative of I J. I will write it as a 1/2 of epsilon I j k, derivative of I, derivative with respect to j, plus 1/2 of epsilon I j k, derivative of I, derivative with respect to j. Okay, and then I can swap these two together. Then I will get 1/2 of epsilon I j k, derivative of I, derivative with respect to j, minus 1/2 of epsilon I j k, and that will be derivative of j, derivative with respect to I. Okay. Yes. JKI. And easily you can expand them. So you will get the summation of I, j, and k, and then you will get 1/2 of epsilon I j k, derivative of I, derivative of j a k, and then minus 1/2 of summation of epsilon j I k, derivative of j, derivative of k, sorry, I of a k. Then swap these together, you will get I derivative of j, assuming that is symmetric way. And the indexes, they're just a normal one, so the summation of the two will be equal to 0. That's one case. The second case that I can tell is the curl of A, which is the last one that we just described. Do you look at the IS component? So you will get epsilon I j k, the summation on j and k. Then you have derivative of j, curl of A, the case component. Then you have epsilon j k, epsilon I j k, derivative of j. Then that will be equal to m and n. The case component will be epsilon k m n, derivative with respect to m and a n. Then you will have I k m n. Then you have epsilon I j k, epsilon k m n, derivative with respect to j, derivative with respect to m of a n. And well, if you remember, we had the summation of epsilon I j k, epsilon m n k, summation on k, that was equal to delta of I m, delta of j m n, minus delta of I n, delta of j and m. And then what we need to do, we need to swap these together twice. Okay. And then for each time we have a minus sign, then since we are swapping twice, then the result will be the same. So it will be m, n, and k with a positive sign. So, and if you write it down, that will be summation on j, k, m, and n. Then we will get epsilon I j k, epsilon m, n, k, then derivative of j, derivative with respect to m, which is very beautiful. It shows that the derivatives are acting on on a vector, and the summation on k, we can take it out, so it will be j, m, and n. And then we have summation on k, epsilon I j k, epsilon m n k, derivative of j, derivative of m a n, and that is equal to delta of I m, delta of j n, minus delta of I n, delta of j and m. Then the summation on m goes away because we have a delta. Summation on n goes away, we will have a delta. So we have a summation on j only. A summation on j. Then all m will be replaced by, that will be j all m will be replaced by I, and all n will be replaced by j. Then the second term we have all n will be replaced by I, and all j will be replaced, all m will be replaced by j. I. Okay. So then we have the summation on j, I j aj minus the summation on j, the second derivative of j ai. So indeed, that is I summation on j aj derivative of j of aj. Then the other one will be j second derivative of j acting on ai, which indeed this is del dot a, and that's the is component, and this one also is Laplacian, and that's the is component. So what you will get the derivative with respect to xi of divergence of a minus Laplacian of ai. So what was that? Was the is component of the expansion. So the is component, which was curl of a, the is component. So if you expand it, you will see that you have it for 1, 2, and 3, and then you will get for all of the components. So I think I'm done. I can give you a few examples, but I think is going beyond the time that we had. Next lecture, I will go with Maxwell equations, and I will drive the wave equation and some of the meanings of those equations. So I will encourage you to get ready for the next lecture. I will encourage you to just look at the Maxwell equations in a simple way, understanding what are the meanings, what is the electric field, magnetic field, the charge density, the current densities, epsilon naught, mu naught, and the time derivative. Just having an idea about that. And next lecture, we will go, let's say 30 minutes only talking about Maxwell equations and how to get a scalar potential, vector potential, and the meaning of them, and going with the wave equations. So I think the lecture is done. I'm open for the questions.
So there's a question: is there any physical meaning for Laplacian?
Well, yes. In the you will see when we go with the we will go with the 4 vectors. Yes, the Laplacian will have a meaning, which is an invariant operator, and which describes the wave equation essentially.
Perfect. Is the curl of a vector in a certain point a valid concept? I can't imagine rotation in one point.
Or rotation around that point axis.
Mm-hmm.
Okay.
Yep. Okay. So there is a question outside the scope. Some theories like modern electrodynamics predict that divergence of magnetic field is not zero. In other words, there are magnetic monopoles. If this is true, does it mean that this equation, divergence of V equal to 0, is false?
Yes.
Okay.
Yeah, indeed, there are Dirac monopole, which is Dirac had the equation for it, and this beautiful equation essentially. But so far we have not observed any things beyond the divergence of B equal to 0. We did not find that. Well, let me tell you one thing. I mean, the nature is not about your equations. There are so many beautiful equations in the world and theories. The nature is nature. It is its own law. So, well, yes, of course, I agree with you that there are many beautiful equations which they modify the Maxwell's, and they will tell you also Fulton has a mass, and also the monopole exists. But when we look into nature, and we didn't find them.
Perfect. Can you give an example of divergence of curl of a vector in physical world?
Divergence of a curl. Didn't we drive that?
We did. It's 0
Yes,
usually.
we drive that, yes. And you will see that essentially these look like a magnetic field. And you will see that later on, that is because that's equal to 0.
Perfect. About the 7th edition for the assignment, I didn't check it. I'd recommend you use the 6th edition to make sure it's safe, as mentioned in the assignment. Okay, unit vector is constant in Cartesian coordinate system. Its derivative is 0, but in another coordinate system, we have non-constant unit vector that its derivative is non-zero. What is the reason?
Because the orientation is changing. The orientation is changing in that vector. So, for example, I will always encourage students, I mean, if you are not feeling comfortable with that, I will always encourage you to write in the Cartesian coordinates. So, for example, we say r hat, right? I just drive the r hat for you. And what is r hat in the Cartesian coordinate? Is cosine of theta z hat plus sine of theta cosine of phi. Let's go the other way. Sine of phi y hat plus sine of theta cosine of phi x hat. So assuming that your x hat, y hat, and z hat, but if you go to spherical coordinate, in spherical coordinate that you have it here, for example, then your r hat can be anywhere. And what is the position of this r hat? It can be theta with respect to this angle, and it can be angle of phi with respect to x-axis, okay? And that's r hat. The magnitude of r hat is fixed, is 1. But what is happening with the orientation? R is depending, or R depends on theta and phi. Is not constant. So when it's not constant, I'm expecting that if you take the divergence, what was the question? So so if you take the derivatives, is not 0. Well, that's it. And we will describe these coordinates in chapter 2 next week for sure.
Perfect. And someone is asking if you can intuitively explain why the divergence of curl is 0. Like,
let's wait for the next lecture, okay? Which will give an example of the magnetic field.
perfect.
Because the divergence,
sorry.
what was the divergence? Was a source, right? Yeah. Okay.
Okay. I think that's all on the question side. Thank you so much.
Yeah, of course. And also let me stop the YouTube.